Welcome to Lecture 5. Today we will start with our next focus, benzene and other aromatic compounds. But before we start, we will briefly revise what we learned in the last lecture. Last lecture we saw several oxidational reactions of alkenes, and here I would like to briefly summarize which products can result under which reaction conditions. First of all, we saw that alkenes react with peroxycarboxylic acids to form epoxides. These epoxides can subsequently be transformed towards anti-1,2 diols by acid or base catalyzed ring opening reactions. Conversely, if the alkene reacts with osmium tetroxide, we get selectively syn-1,2 diols. And we get the same products, so also syn-1,2 diols, by the reaction of the alkene with potassium permanganate in a cold reaction mixture. Conversely, if we conduct the same reaction, not in a cold reaction mixture, but at room temperature or even higher temperatures, we will get ketones and carboxylic acids instead of the syn-1,2 diols. And if the alkene reacts first with osmium tetroxide, and then with periodic acid as oxidizing agent, we will end up with ketones and aldehydes. Ketones and carboxylic acids are also formed by the reaction of alkenes with ozone and subsequent oxidizing conditions. However, if we use reducing conditions instead of oxidizing conditions after the reaction with ozone, we will end up with ketones and aldehydes. Besides these oxidation reactions of alkenes, we also had a closer look on alkynes, and we saw that alkynes react very similar to alkenes. And similar to alkenes, alkynes can also react in electrophilic addition reactions, and we discussed two reactions more detailed. So first we saw that the addition of hydrogen halides is regioselective, and we produce halogenoalkenes. And according to the Markovnikov rule, the proton will always act in that way that the more stable vinyl cation is formed. And more stable means here that the secondary instead of the primary vinyl cation is formed. Furthermore, we also learned that the production of aldehydes from terminal alkynes is also regioselective. And this reaction is a four-step reaction, and more specifically, we can say it's a hydroboration followed by oxidation. The first step is a hydroboration, which is a syn addition, and we generate vinyl borane. The second step, two further hydroborations are conducted until we end up with the trivinyl borane. The third step is the production of an enol, and enol means that the hydroxide group is attached to a carbon atom, which is part of a carbon-carbon double bond. And the step is also an oxidation step. And the last step is the tautomerism step. Here we have an equilibrium between the enol and the aldehyde. And as you can see on the different length of the arrows, the aldehyde is thermodynamically favored. And with these reactions, we finished the chapter of alkenes and alkynes. And we will now start with the chapter of benzene and other aromatic compounds. Benzene has the formula C6H6, and it consists of 6 sp2 hybridized carbon atoms that link together to form a planar ring. And this ring is hexagonal, and all carbon-carbon-carbon bonds have an angle of 120 degrees. Moreover, all carbon-carbon bonds are 139 picometers long, and this value is between a normal value for a carbon-carbon single bond, which is 154 picometers, and the value for a carbon-carbon double bond, which is 134 picometers. And each of the sp2 hybridized carbon atom has an unhybridized p orbital at a right angle to the ring plane. This is indicated here. Each of these unhybridized p orbitals contain one electron. And as you can see here, all these p orbitals are close enough to the neighbor p orbitals so that they can overlap and form one ring above and one ring below the ring plane. And in these rings, The electrons are now delocalized, that means they are spread out and not localized at a certain carbon atom. And these electrons are also called pi electrons. So if we draw a benzene molecule like this with a ring inside, we want to demonstrate that the electrons are delocalized in the pi bond. However, if we want to show the movement of electrons, for example, during a reaction, we always use the Kekulé structure for benzene, which is shown here. In the Kekulé structure, we draw benzene with alternating carbon-carbon single and carbon-carbon double bonds. Important to know is that the Kekulé structure only represents one resonance structure of benzene, and the description of benzene with alternating carbon-carbon single and carbon-carbon double bonds is not true. So what is important, if we draw the Kekulé structure, we have to keep in mind that according to the Kekulé structure, the carbon-carbon double bond would be shorter than the carbon-carbon single bond, but in benzene, all bonds are equally long. Moreover, you would expect that the carbon-carbon double bond would react in electrophilic addition reactions like we saw for alkenes, but that is not the case. So benzene undergoes electrophilic substitutional reactions and no electrophilic addition reactions. And also important is that you know that benzene is much more stable than the Kekulé structure suggests, because the pi electrons are delocalized and there are not only 3 pi bonds. So what is important to know is that benzene behaves different to an unsaturated hydrocarbon, and benzene shows a special stability and reactivity.